Hi everyone. In this video, I will be coding a convolutional neural network from scratch to classify images. This is in preparation for my taking of the Google Tensorflow certification, and so I will be going through some key concepts which are vital for taking the certification. The certificate tests a developer's foundational knowledge of integrating machine learning into tools and applications. The certificate program requires an understanding of building TensorFlow models using computer vision, convolutional neural networks, natural language processing, and real-world image data and strategies. It costs $100 to take the exam, and a candidate will have 5 hours to complete the exam. In addition, the candidate has to use PyCharm to code. Currently, it is the start of April 2024. And TensorFlow has an update with a plan to evaluate the program and will be closing down the exam. The last day to register to take the exam is April 30th, 2024, and the last day to take it is May 31st, 2024. Credentials will be valid for 3 years after passing the exam. As such, I have given myself a tall task of learning and demonstrating an understanding of coding in a very short period of time, which is 1 month. So I have signed up for the Deep Learning AI TensorFlow Developer Program from Coursera to speed up my learning, and also to code out to practice and test my understanding as well. So for today's video, I will be attempting to cover some key concepts from the candidate's handbook, which is to build and train neural network models using TensorFlow 2.x to do image binary classification. You may refer to the details of it on their website. As of the date of making this video, I have not taken the exam, so I really do hope that whatever I will be doing helps in the preparation of the exam. So the main topics that I would like to cover today are setting up the test environment and doing a walkthrough of some of the key concepts that they might be testing for computer vision binary classification. Let's get started. The candidate's handbook provides instructions on how to set up the test environment. We will be using PyCharm and Python version 3.9 for the test. Download them from the official websites and install them. Take note of the directory for the Python installation, as we will need to switch it for the Python interpreter. Once we start up the PyCharm and open a file, we will get this view. On the bottom left of the screen, there are a few icons, which will bring up different screens for interaction. The first is the Python console, which is quite standard. The icon below is the packages, which we will be using to install the Python packages. The last one which we might be using is the terminal. Next, we will change the interpreter to meet the test requirements. If you have downloaded the most updated version, the pre-installed version is Python 3.12. So we would have to change it to 3.9. To change it, we can click on the gear icon at the top right corner and go to Settings. It will bring up a pop-up screen and we will navigate to the project we are in. Select Python Interpreter and Add Interpreter. This will bring up another screen, and using the directory path where we stored our installed Python 3.9, we will select it using the environment options available and click OK. Alternatively, you can check the bottom right corner, and clicking it will allow you to change the interpreter as well. To check that you have the correct Python version, you can run print system version in the console to confirm. Next, we will download the plugin required to run the test. Go to the gear icon at the top right corner and select Plugins. Search for TensorFlow Developer Certificate and install it. When you need to start the exam, click on it to begin. Lastly, we would need to install the libraries which will be used. Though it is mentioned that the exam framework will install them, you can install them first for practice to simulate the exam environment. To install them, head down to the bottom left of the screen and select Python packages. It will bring up a list of and search for the packages. For example, if I search for NumPy and select Install, it will bring up a list of versions. Select and install version 1.24.3. Do the same for the rest of the libraries, and we are all set to start practice. Although the exam is in PyCharm, I will be running the codes in Google Colab instead, as I find it easier to visualize the results here. Not to worry, the codes will work fine in PyCharm as well. Just something to note, Try to run the Google Colab notebook with a GPU, as it will help to speed up the training. So, in today's session, we will be covering the following key concepts, which are firstly, to use TensorFlow dataset to load data. Pre-process the data using augmentation techniques. Create a callback function. Building a model with convolution and pooling layers for computer vision binary classification. Plotting accuracy and loss metrics charts. And finally, to peel and look at the intermediary layers to see what features are being extracted. There is quite a bit to cover, so let's get started. We will start by importing the libraries that we need to use. NumPy is used to manipulate the numerical arrays, and the various TensorFlow libraries are used to build the model and load the data. We will also import matplotlib to plot the charts, and random to do a random select later on. We will also import SSL and set the contexts. This is not really needed in today's video, but it would be required if there are some certificate issues that you may encounter when downloading data from other sources. This would help to bypass certificate errors. We begin by downloading the dataset. The dataset we will be working on for the binary classification problem is horses or humans, where the model has to classify the images between the two classes, whether the image shows a horse or a human. We load the dataset using tfds.load. We set as supervised to true to return a tuple containing the input data and its labels, and with info equals to true, so that we can view the information on the dataset. We print out the results, and we can see the number of images in the training and validation dataset. We can also see that they have the shapes of 300 by 300 by 3, and scrolling down we can observe more metadata on the dataset. Some of you might have noticed, but I have loaded the dataset twice, once just using tfds.load, and the first line has tfds.numpy, to convert the output from loading the data into numpy arrays. This would help to make things easier, as I feel that it's easier to work with numpy arrays as compared to tensors. As such, we will be using the arrays for our model training later on. With the output from tfds.load, we can run the command to show examples to inspect the data visually. So we can see some sample horses and humans, where horses are labeled as 0 and humans are labeled as 1. So the data is loaded now, but it would be good to mix things up by having even a greater variety of data. How do we do that? We will pre-process data further by performing augmentation. We will call upon the image data generator class to help us with it. Here, we will pass several arguments to the generator to help to randomize the pictures. We can rescale them, rotate the pictures within a specified range, and adjust the pictures with shear, zoom and flipping. Do note that we will only specify them for the training generator, but not the validation generator, as those are for training purposes. We will scale them by a factor of 255, as it is common practice to do so, and it improves model performance. We will specify the X and Y data and labels and call the flow method to pass the data through the generators. Another good thing about using the generator is that the images are transformed in memory and they are not stored. This means that they are transformed as they flow through the generator and pass into the model, and they do not take up space. Now, we will build the model. This will be a simple model with a few layers. We will implement 3 convolution 2D layers and 3 pooling layers, followed by a flatten, and another layer followed by the final layer with 1 neuron with a sigmoid activation function, since it is a binary classification. From the printed summary, we can see how the image gets processed at each layer, getting smaller through the convolution and pooling layers. Next, we will create a callback function which we will pass into the fitted model later on. The function will be activated at the end of each epoch run, and we have specified to stop the training when accuracy is above 80% or if validation accuracy is above 60%. Finally, we can compile and train the model. We will be using the Atom Optimizer and set the loss function to binary cross-entropy for binary classification. We will fit and train the model, passing the generators into it and train for 10 epochs. This might take a while, so I will skip till the training is completed. So, the training is now completed. The callback worked, as we can see that instead of training till the end of 10 epochs, it stopped at the 4th epoch where the accuracy is above 80%. It so happens that the validation accuracy is above 60% as well. We will now plot the accuracy and loss charts for the training and validation runs. We will extract them from the history variable which was saved from the model training. We will plot them with red and blue lines and label accordingly. We can take a quick look at the plots and move on. We have come to the last key concept to cover, which is to look at the features that are extracted at each layer of convolution and pooling. For this, we will have to extract the layers at each output and create a new model for visualization. We will randomly select a training image and pass it through the new model for prediction. Next, we will display it visually layer by layer with the name so that you can identify the layers that pick up the feature extractions. The following lines are just to reshape and resize them, and to select only the convolution and pooling layers for display. And there you have it, the different convolution and pooling layers with their respective feature extractions. And that's the end of this video. To recap, we have gone through the key concepts of using TensorFlow dataset to load data. Pre-process the data using augmentation techniques. Create a callback function. Building a model with convolution and pooling layers for computer vision binary classification. Plotting accuracy and loss metrics charts. And lastly, to peel and look at the intermediary layers to see what features are being extracted. Hope that it is useful to you as a reference. So, what are your thoughts on it? Feel free to comment in the comment box down below. If you liked this video and would like to see more content of this nature, please be sure to like and subscribe as well. Thanks for watching, and until next time.